Utilizing the knowledge that you gained in previous chapter, you will have chances to apply chemical equilibrium to acids and bases in this chapter. Before handling the in-depth areas of acid-base equilibria, I'd like to start with general characteristics of acids and bases. Acids have sour taste and turn blue litmus paper red. Several examples of acids are hydrochloric acid, sulfuric acid, nitric acid, acetic acid, citric acid, carbonic acid, hydrofluoric acid, and phosphoric acid. Conventionally, acidic hydrogens or protonic hydrogens are written first in the chemical formula, which are represented by the first hydrogens in red in each formula of the listed acids. There are three acidic hydrogens in the formula of citric acid, meaning citric acid is a triprotic acid. Take a note that additional 5 hydrogens after the 3 acidic hydrogens in the formula are not acidic. Bases have bitter taste, feel slippery, and turn red litmus paper blue. Some examples include sodium hydroxide, potassium hydroxide, sodium bicarbonate, sodium carbonate, and ammonia. Please take a note that not all bases have hydroxide ion or OH- ion in their formula. I will discuss more about it in the following slides. How do we know whether a chemical substance is acidic or basic? There are 3 ways of defining acids and bases. The first one was suggested by savant Irenaeus, often called Irenaeus' acids and bases. In his definition, an acid is a substance that increases the concentration of H plus ions when dissolved in water. Hydrochloric acid releases H plus ion or proton and increases the concentration of protons when dissolved in water. A base is a substance that increases the concentration of OH- ions when dissolved in water. Sodium hydroxide releases hydroxide ion and increases the concentration of hydroxide ions when dissolved in water. Irenaeus' definition of acid and bases is very limited in that substances should be dissolved in water and become aqueous solutions to be defined as acids or bases. The second way of defining acids and bases was suggested by Johannes Bronsted and Thomas Lowry, often called Bronsted-Lowry acids and bases. Please be aware that H plus ion is also called proton because the ion has only one proton without any neutrons and electrons. In reality, the proton does not exist alone in the form of H plus in aqueous environment. Instead, it combines with water molecule because the water molecule contains lone pairs of electrons. This combined form is called hydronium ion, and in many cases associated with acids and bases, the hydronium ion will be used in place of proton. Let's take a look at a proton transfer reaction. The proton of hydrochloric acid is transferred to water molecule, forming hydronium ion and leaving chloride ion behind. This whole process is represented by this chemical equation. Based on Bronsted-Lowry's definition of acids and bases, an acid is a substance that can donate a proton to another substance. It is also called proton donor. A base is a substance that can accept a proton, and it is also called proton acceptor. In the reaction of hydrochloric acid and ammonia, hydrochloric acid donates a proton to ammonia illustrating hydrochloric acid as an acid and ammonia as a base. Please take a note that the NH3 cannot be defined as a base by Arrhenius' definition because it does not release hydroxide ion. However, it is defined as a base by Bronsted-Lowry's definition of acids and bases because the NH3 accepts a proton. Based on Bronsted-Lowry's definition, acid-base reactions are not limited to aqueous involvement, and they can be defined even in gas phase. Let's take a look at another acid-base reaction. In this reaction, NH3 can be defined as an Arrhenius base, even if NH3 does not contain hydroxide ion in its structure. It is because the ammonia produces hydroxide ions and increases the concentration of hydroxide ions as it goes through the reaction. The ammonia is also defined as Bronsted-Lowry base because it accepts a proton from the water molecule. Please keep in mind that acid and base always work together to transfer a proton, which makes sense because if there is a substance that donates a proton, there should be another substance that accepts that proton. For a molecular or ionic substance to be a Bronsted-Lowry acid, it must have a hydrogen atom to be lost as an H plus ion. For a molecular or ionic substance to be a Bronsted-Lowry base, it must have a non-bonding pair of electrons to bind the H plus ion. Let's take a look at the dissociation process of HCl in water. A proton from HCl is donated to water molecule. This makes the water molecule a base. Let's take a look at the dissociation process of ammonia in water. A proton from the water molecule is donated to ammonia molecule. This makes the water molecule an acid. Interestingly, water molecule acts like a base in certain cases, while it also acts like an acid in other cases. Molecules like water that acts like both acid and base are called amphiprotic molecules. One unique and important concept that you should be aware of in Bronsted-Lowry acids and bases is conjugate acid-base pairs. Let's look at the dissociation process of an acid HX in water. Double arrow indicates that it is an equilibrium process. In forward reaction, HX acts as an acid because it donates a proton to H2O, and H2O acts as a base because it accepts the proton from HX. Now, in reverse reaction, X minus acts as a base because it accepts a proton from hydronium ion, H3O plus, while H3O plus acts as an acid because it donates the proton to X minus. An acid and a base such as HX and X minus that differ only in the presence or absence of a proton is called a conjugate acid-base pair. Please be aware that every acid has a conjugate base and every base has a conjugate acid. In the dissociation of nitrous acid HNO2, H2O is a base because it accepts a proton from HNO2. Conjugate base of HNO2 is NO2 minus, and conjugate acid of H2O is H3O plus. Don't forget that conjugate acid-base pair differ only in the presence or absence of a single proton. Let's try some practice problems. What is the conjugate base of each of the following acids? Perchloric acid, hydrogen sulfide, phosphonium ion, and bicarbonate ion. An acid should have at least one acidic hydrogen, and its conjugate base is the substance formed by removing that single acidic hydrogen from the acid. That is why conjugate acid-base pair differ only in the presence or absence of a single proton. With that in mind, conjugate bases of the four acids are ClO4 minus, HS minus, PH3, CO3 2 minus. Remember that you should take care of charge of the substance after the removal of the acidic hydrogen, because acidic hydrogen or proton has a charge of +1. Let's move on to the second problem. The hydrogen sulfide ion is amphiprotic. Write an equation for the reaction of HSO3- with water, in which the ion acts as an acid. Since the hydrogen sulfide ion acts as an acid, it should donate a proton to water molecule, making hydronium ion and leaving SO3 2- ion behind. The equation should be written like this. Once again, please be aware of the change of the charge of the species after removing or adding an H+ ion. Let's move to B. Write an equation for the reaction of HSO3- with water, in which the ion acts as a base. In both cases, identify the conjugate acid-base pairs. Since the hydrogen sulfide ion acts as a base this time, it should accept a proton from a water molecule, leaving OH- ion and H2SO3 behind. The equation should be written like this. In the first equation, HSO3- is the acid and H2O is the base, and conjugate base of HSO3- is SO3 2-, and conjugate acid of H2O is H3O+. And I want you to identify the conjugate acid-base pairs for the second equation by yourself. The strength of acids and bases are very different and dependent on multiple factors. Look at a list of acids and their conjugate bases on the right. Very important trend is that the stronger an acid, the weaker is its conjugate base. The stronger the base, the weaker is its conjugate acid. Strong acids are completely dissociated in water. Their conjugate bases are quite weak. They are so weak and they are not even called bases. Strong bases are also completely dissociated in water. Their conjugate acids are quite weak, and they are not even called acids. Weak acids are only dissociated partially in water. Their conjugate bases are also weak bases. Please take a note that weak acids and their conjugate bases are weak but retain non-negligible acidity and basicity and have various strength in acidity and basicity depending on many factors. And I am going to cover the details about those factors later. Look at this proton transfer reaction. An acid HX donates a proton to H2O, forming a hydronium ion and leaving an X- ion behind. Obviously, H2O acts as the base because it accepts a proton from HX. Look at the right side of the equation. X- is the conjugate base of HX, and in the perspective of reverse reaction, it accepts a proton from the hydronium ion. So There are two bases existing in this reaction, water and X minus. The question is whether the reaction proceeds to the right or to the left. Which one is more favorable? It depends on the relative strength of the two bases. If H2O is a stronger base than X minus, the equilibrium will lie to the right because H2O has greater strength to remove the proton than X minus does. One example is the dissociation of HCl in water. There are two bases in the reaction, H2O and Cl-. You may verify their relative strength shown in the table of the previous slide. H2O is a stronger base than Cl-. As a matter of fact, the basicity of Cl- is negligible, and it is not even called a base. So the reaction lies completely to the right. If X- is a stronger base than H2O, the reverse is true, or the equilibrium will lie to the left. An example for that is the dissociation of acetic acid in water. There are two bases, H2O and C2H3O2- or acetate ion. Based on the table shown in previous slide, the acetate ion is the stronger base than water, so the equilibrium lies more to the left. In summary, proton transfer reaction is governed by the relative ability to abstract protons. In every acid-base reaction, the position of the equilibrium favors transfer of the proton to the stronger base. Let's try a practice problem. Predict the products of the following acid-base reactions and also predict whether the equilibrium lies to the left or to the right of the equation. Check the relative basicity of O2- or oxide ion or water from the table in previous slide. Since oxide ion is stronger base, it will take a proton from water molecule, making water act as an acid, which would produce two hydroxide ions. In reverse reaction, one of the two hydroxide ions serves as an acid while the other serves as a base. So there are two bases in the reaction, O2- and OH-. Which one is stronger base? Since O2- is the stronger base, the equilibrium lies to the right. Water is an amphiprotic molecule, which means that it acts as both an acid and a base. Here are two water molecules. One of them acts as an acid that donates a proton, and the other one acts as a base that accepts that proton. So the two water molecules react and produce one hydronium ion and one hydroxide ion. This process is called autoionization of water, and it is represented by this equation. Since a hydronium ion is equivalent to a proton, the equation can be simplified by this. A single water molecule is split into a proton and a hydroxide ion. And once again, it is the autoionization of water, and it is an equilibrium process which is represented by a double arrow. The equilibrium constant expression is written as the concentration of H3O plus times the concentration of OH minus, or simply the concentration of H plus times the concentration of OH minus. Please be aware that the reactant H2O is the pure solvent, and it is not included in the equilibrium constant expression because its activity is 1. The equilibrium constant value for this process is 1.0 times 10 to the negative 14th. You must memorize this value. This Kc is specifically denoted as Kw. The Kw is called ion product constant for water. The autoionization of water is valid for any dilute solute solution. The value of Kw can be used to calculate the concentration of H plus if the concentration of OH minus is known, or the concentration of OH minus if the concentration of H plus is known. We can calculate the concentrations of proton and hydroxide ion in a neutral solution at the standard temperature 25 Celsius. You may use the Kw expression and Kw value to find the concentration of each. Since autoionization of water produces protons and hydroxide ions by 1:1 mole ratio, and if you put the concentration of proton to X, then the concentration of hydroxide ion should be also X. This makes X squared, and it is equal to 1.0 times 10 to the negative 14th. The X, which is the concentration of H plus and also the concentration of OH minus, is 1.0 times 10 to the negative 7th molar. Let's take a practice problem. Calculate the concentration of proton in a solution in which the concentration of hydroxide ion is 0.010 molar. The Kw value is 1.0 times 10 to the negative 14th. Plug the given concentration of hydroxide ion into the Kw expression and solve the equation for the concentration of proton, and you will get 1.0 times 10 to the negative 12th molar. pH is used as a measure of acidity or basicity of a substance, and it is defined as negative log of the molar concentration of proton. Autoionization of water shows that the concentration of proton in pure water is 1.0 times 10 to the negative 7th molar. The pH of pure water is then negative log 1.0 times 10 to the negative 7th, which is equal to 7.00. Please take a note that pH does not have any unit. An acid has a higher concentration of proton than pure water, or an acid has a pH less than 7. If the concentration of proton of a solution is 1.0 times 10 to the negative 3rd molar, the pH of the solution is negative log 1.0 times 10 to the negative 3rd, which is equal to 3.00. Since the pH is less than 7, we know that the solution is acidic. A base has a higher concentration of hydroxide ion than pure water, or a base has a pH greater than 7. If the concentration of hydroxide ion of a solution is 1.0 times 10 to the negative 3rd molar, the concentration of proton can be calculated using the Kw expression and modify the expression with respect to the concentration of H+, which is Kw over the concentration of OH-. Kw is 1.0 times 10 to the negative 14th, and the concentration of OH- is given as 1.0 times 10 to the negative 3rd. Then the concentration of H+ is equal to 1.0 times 10 to the negative 11th molar. Now, you're ready to calculate the pH. That is, negative log 1.0 times 10 to the negative 11th, and it is pH 11. Since the pH is greater than pH 7, we all know that the solution is basic. Look at the list of substances that you may encounter on a daily basis. The concentration of proton, pH, pOH, and the concentration of hydroxide ion of each substance are also listed. You may easily notice that the pH of lemon juice is approximately 2, which is acidic. The pH of household bleach is about 12.5, which is basic. We can use the pH and quantify the acidity or basicity of a substance. The more acidic, the lower pH. The more basic, the higher pH. Let's take a couple of practice problems. In a sample of lemon juice, the concentration of H plus is 3.8 times 10 to the negative fourth molar. What is the pH of the solution? pH equals negative log 3.8 times 10 to the negative fourth, and it is equal to 3.42. Let's move on to the next problem. A sample of freshly pressed apple juice has a pH of 3.76. Calculate the molar concentration of proton. The pH is equal to negative log of the concentration of H plus, which is also equal to 3.76. The molar concentration of H plus is anti-log of minus 3.76 or 10 to the negative 3.76, which is 1.7 times 10 to the negative fourth molar. Just like the definition of pH, the pOH is defined as negative log the molar concentration of hydroxide ion. Kw is expressed as the concentration of H plus times the concentration of OH minus, which is equal to 1.0 times 10 to the negative 14th. You may add negative log to all sides of the equation. The middle portion of the equation can be split into negative log H plus plus negative log OH minus, and far right side of the equation is 14. The negative log can be replaced by the lowercase letter p, which simplifies the equation to pKw equals pH plus pOH equals 14. This equation is very useful and may save you much time in problem solving. If you know the pH of a solution, you can find easily the pOH value of the solution. Practically, solution pH can be measured with either pH meter or an acid-base indicator. Measuring pH with an acid-base indicator is less accurate because you determine the solution pH approximately based on the color change of the solution. On the right, you can see 7 representative acid-base indicators and the pH range that bring about color change of the solutions. There are 7 strong acids that you must memorize. The first 6 strong acids are monoprotic acids. They are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, and perchloric acid. The last acid is sulfuric acid, and it is a diprotic acid. A strong acid dissociates completely, and it is not an equilibrium process. Let's see how the nitric acid is dissociated in water. It dissociates and forms a hydronium ion and a nitrite ion. The complete ionization is not an equilibrium process, which is represented by a single arrow. This further indicates that nitric acid is a strong acid. The equation for the dissociation of nitric acid can be simplified by this. Please take a note that both equations should be balanced no matter it is simplified or not. Let's take a practice problem. What is the pH of a 0.20 molar solution of nitric acid? Since the nitric acid completely dissociates into proton and the nitrate ion, the initial concentration of nitric acid is equal to the concentration of proton, which is 0.20 molar. The pH is negative log 0.20, which is equal to 0.70. Strong bases are the ones that dissociate completely in water. The examples of those that ionizes completely are sodium hydroxide, potassium hydroxide, and calcium hydroxide. Those are three representative hydroxides of alkali metals and alkaline earth metals. Calculate the pH of a 0.0011 molar solution of calcium hydroxide. Since 1 unit of calcium hydroxide releases 1 Ca2 plus ion and 2 hydroxide ions, the concentration of hydroxide ion is twice as high as the concentration of Ca2 plus ion, or the initial concentration of calcium hydroxide. So the concentration of hydroxide ion is 2 times 0.0011 molar, which is equal to 0.0022 molar. The pOH of the solution is negative log 0.0022, which is equal to 2.66. The pH of the solution can be determined by modifying the equation of pH plus pOH is equal to 14. Then the pH is equal to 14.00 minus pOH, and the pH of the solution is 11.34. As I said previously, hydroxides of alkali metals and alkaline earth metals are strong bases. But please be aware that most of alkaline earth metal hydroxides have very limited solubility. Those are beryllium hydroxide, magnesium hydroxide, calcium hydroxide, and strontium hydroxide. Strongly basic solutions are created by substances like metal oxides that react with water to form hydroxide ions. Examples of strongly basic metal oxides are sodium oxide and calcium oxide. Once they dissolve in water, they release an oxide ion or O2- ion. This oxide ion receives a proton from water molecule and forms a hydroxide ion, leaving another hydroxide ion behind and producing total of 2 hydroxide ions. Ionic hydrides and nitrides are also basic. H- ion or hydride ion takes a proton from water molecule, forming a gaseous hydrogen molecule and leaving a hydroxide ion behind. Likewise, nitride ions takes 3 protons from 3 water molecules and forms ammonia molecule, leaving 3 hydroxide ions behind. Both cases produce hydroxide ions and make solutions highly basic. Weak acids are partially ionized in aqueous solution. Partial dissociation or ionization is an equilibrium process which is represented by a double arrow like this equation. The equilibrium constant Kc for the dissociation of a weak acid Ha should be H3O plus times A minus divided by Ha. The chemical equation can be simplified by using proton in place of hydronium ion. The corresponding Kc for the simplified equilibrium process is H plus times A minus divided by Ha. This specific equilibrium constant for the dissociation of weak acid is denoted as Ka, and it is called acid dissociation constant. How is the Ka value related to the strength of an acid? The larger the Ka, the stronger the acid. How can you rationalize this trend? Based on the Ka expression, to make the Ka larger, you should have higher concentration of proton, which would make the acid stronger weak acid. Look at the table on the right. It is a list of weak acids and their Ka values. The Ka values increase from the bottom to the top. It further implies that hydrofluoric acid is the strongest weak acid from the listed acids. The pH of the acid solution allows you to calculate the Ka value. Let's take a practice problem. Lactic acid has one acidic hydrogen. A 0.10 molar solution of lactic acid has a pH of 2.44. Calculate Ka value. You can calculate the equilibrium concentration of proton from pH value. Since the pH of the solution is 2.44, the negative log of H plus is equal to 2.44. Then the equilibrium concentration of proton is anti-log negative 2.44 or 10 to the negative 2.44 molar, which is equal to 3.6 times 10 to the negative third molar. You should construct ICE chart for most of the problems that are associated with chemical equilibrium, like this one. Please keep in mind that only middle row of the chart or changes in concentrations follows stoichiometric rules. Initial concentration of the weak acid is given, which is 0.10 molar, and the initial concentrations of H plus and lactate are 0 because this is before the acid is dissociated. The equilibrium concentration of proton was calculated already, that is 3.6 times 10 to the negative third molar. Then you can fill the rest of the blanks. Once again, don't forget only middle row of the chart follows stoichiometric rules. Since mole ratio of reactants and products is 1 to 1 to 1, you are losing a certain molarity of reactant, and at the same time you are gaining the same molarity of the products. Equilibrium concentration of each species can be determined by combining initial concentrations and changes in concentrations. So the values for the rest of the blanks are like this. Since equilibrium concentrations of all substances were determined, now you're ready to plug them into Ka expression and calculate the Ka value. The calculated Ka value is 1.4 times 10 to the negative fourth. Please take a note that the Ka does not have any unit because it is an equilibrium constant. More specifically, acid dissociation constant. Let's move to the next question. What percentage of the acid is ionized in this 0.10 molar solution? Remember, percent ionization is part per whole times 100. That is equilibrium concentration of proton is the quantity of the proton dissociated from the weak acid. So the percent ionization is equal to equilibrium concentration of H plus over initial concentration of the acid times 100. The percent ionization is 3.6%. In a reverse manner, acid dissociation constant Ka can be utilized to calculate the pH of a solution. Here is an example. What is the pH of 0.30 molar acetic acid solution? The Ka of acetic acid is 1.8 times 10 to the negative fifth. The first step you should take is to write the equation for the ionization of the acid. Remember, the ionization of a weak acid is always an equilibrium process. The chemical equation shows that acetic acid ionizes into a proton and an acetate ion. The second step is to write up the Ka expression like this, based on the equation for the ionization equilibrium of acetic acid. We will use it later after the equilibrium concentrations of all substances are determined. And now you should construct an ICE chart like this. Initial concentration of acetic acid is given as 0.30 molar, and the initial concentrations of proton and acetate ion are zero because it is before the acetic acid ionizes. Since the equilibrium concentration of proton is not determined yet, let's put it to x molar. The change in the concentration of proton should be also x molar. Only the middle row of the chart follows stoichiometric rules. Then the remaining blanks in the middle row can be filled based on 1 to 1 to 1 mole ratio. Don't forget to add negative sign for the concentration change of the reactant because it is the one to be depleted as the reaction progresses. Then the equilibrium concentration of acetic acid is 0.30 minus x molar. The equilibrium concentrations of both proton and acetate ion are x molar. Now, plug the equilibrium concentrations into the Ka expression, then you will get Ka equals x times x or x squared over 0.30 minus x. This is equal to 1.8 times 10 to the negative fifth. This equation seems a little complicated. You may simplify the equation only if x is much smaller than 0.30. If x is much smaller than 0.30, the denominator can be approximated from 0.30 minus x to simply 0.30. Since x is too small, the subtraction does not affect the initial value of 0.30. But once you determine the x, you should always come back here and verify whether the x is actually much smaller than 0.30. Conventionally, x must be less than 5% of 0.30 or x must be less than 0.015. If x is greater than 5% of 0.30, then you should use a quadratic formula. The Ka expression is now much simplified to x squared over 0.30, which is equal to 1.8 times 10 to the negative fifth. Then the x is 2.3 times 10 to the negative third. The concentration of proton is 2.3 times 10 to the negative third molar. The pH of the solution is negative log 2.3 times 10 to the negative third, which is equal to 2.64. Let's calculate the percent ionization of the acetic acid. The equilibrium concentration of proton over initial concentration of acetic acid times 100, which makes 0.77%. The percent ionization is a lot less than 5%. So the approximation is valid. Once again, if it is greater than 5%, you must use the quadratic formula. Just for comparison, let's calculate the pH of strong acid solution in the same concentration, like 0.30 molar HCl solution. Weak acid like acetic acid ionizes partially, which is indicated by a double arrow in the chemical equation. But strong acid like HCl ionizes completely, which is indicated by a single arrow. Because of the complete ionization, the concentration of proton released from HCl is equal to the initial concentration of HCl. So the concentration of proton is simply 0.30 molar, and the pH of the HCl solution is negative log 0.30, which is 0.52. Now take a look. The same concentration of weak acid and strong acid gives rise to very different pH values, indicating strong acid solution makes substantially lower pH, which means much more acidic. Polyprotic acids are the ones that have more than one ionizable hydrogen atoms or acidic hydrogens. Sulfurous acid has two ionizable hydrogens or two acidic hydrogens, as you can see from these two equations, and it undergoes two ionization processes. Please be aware that H2SO4 or sulfuric acid is a strong acid, but H2SO3 or sulfurous acid is a weak acid. The first ionization process produces a proton and bisulfite ion or HSO3 minus ion. The second ionization process produces a proton and sulfite ion or SO3 2 minus ion. Both successive processes are equilibrium processes and have their own Ka values. The first Ka value or Ka1 value is always greater than the second Ka value or Ka2 value. It means that it is always easier to remove the first proton than the second proton. It further implies that H2SO3 is stronger than HSO3 minus. How could it be? It is because if the diprotic acid loses the first proton and the remaining H plus ion and SO3 2 minus ion has increased cation and anion attractions, and it becomes extremely harder to remove the remaining proton. This is reflected on the fact that the Ka2 value is almost 1 million times smaller than Ka1 value. Look at the Ka values of several polyprotic acids. The solid trend is that Ka1 is always greater than Ka2 and Ka2 is always greater than Ka3. If the difference between the Ka for the first dissociation and subsequent Ka values is 1000 or more, the pH generally depends only on the first dissociation. Let's take a practice problem. The solubility of CO2 in pure water at 25 Celsius and 0.1 atm pressure is 0.0037 molar. The common practice is to assume that all of the dissolved CO2 is in the form of carbonic acid, which is produced by reaction between the CO2 and H2O. What is the pH of a 0.0037 molar solution of carbonic acid? Ka1 and Ka2 values are given. Now, let's write the equation for the first dissociation of carbonic acid and construct an ICE chart. Like before, the initial concentration of carbonic acid is 0.0037 molar, and the initial concentrations of proton and bicarbonate ion are 0 molar. Since the equilibrium concentration of proton is not yet determined, let's put it to x molar. Then the change of concentration of proton is also x molar. Now you can fill the rest of the blanks like this. Equilibrium concentrations of all substances should be plugged into the Ka1 expression. That is x squared over 0.0037 minus x, which is equal to 4.3 times 10 to the negative 7th. You may approximate 0.0037 minus x to 0.0037, and the x is 4.0 times 10 to the negative 5th molar, and the x value is less than 5% of 0.0037, so the approximation is valid. The x value is equal to the molar concentration of both proton and bicarbonate ion. Solution pH is negative log 4.0 times 10 to the negative 5th, which is equal to 4.40. In previous slide, you've learned that if the difference between Ka1 value and Ka2 value of a diprotic acid is more than 1000, then the pH depends only on the first dissociation, not the second one. Let's verify the validity of the statement. Second proton of carbonic acid is the one that is released from HCO3- ion or bicarbonate ion. The bicarbonate ion dissociates into H plus ion and CO3- ion. In previous calculation, we determined the concentration of bicarbonate ion, which is 4.0 times 10 to the negative 5th molar. An initial concentration of proton would be the concentration of the proton released from the first dissociation, which is also 4.0 times 10 to the negative 5th molar. Initial concentration of carbonate ion should be 0 because it is before the HCO3- ion dissociates. Let's put concentration change of proton to Y. Then the rest of blanks in the middle row can be stoichiometrically filled like this. Then the equilibrium concentrations of all substances can be calculated by combining the concentrations in the first row and the second row like this. Plug these into the Ka2 expression, and Ka2 value is given as 5.6 times 10 to the negative 11th. If Y is substantially smaller than 4.0 times 10 to the negative 5th, then you may ignore it in addition and subtraction. Then the numbers 4.0 times 10 to the negative 5th on both numerator and denominator are cancelled. Then the Y is 5.6 times 10 to the negative 11th molar. Please take a note that Y is the concentration of proton released from the second dissociation of the acid. The total concentration of proton is the summed concentrations of proton released from the first and second dissociations, which is 4.0 times 10 to the negative 5th plus 5.6 times 10 to the negative 11th molar. Look at the exponents of the first and second concentration of proton. The first one is 1 million times greater than the second one, which implies that the concentration of proton released from the second dissociation does not contribute significantly to the total concentration of proton or the solution pH at all. Weak bases are the bases that partially abstracts a proton from an acid. In this equation, B represents a weak base and water acts as an acid by donating a proton. The Kc expression for this process is Hb plus times OH minus over B. Once again, do not include the concentration of pure solvent like water in the equilibrium constant expression. This particular equilibrium constant for the dissociation of weak base in water is denoted as Kb, and it is called base dissociation constant. In previous slides, you've learned that the larger Ka, the stronger the acid. Likewise, the larger Kb, the stronger the base. This is because Kb value will increase if the concentration of hydroxide ion increases. The dissociation of ammonia in water is a good example. As shown in the equation, ammonia accepts a proton from a water molecule and forms an ammonium ion, leaving hydroxide ion behind. Take a note that the conjugate acid of ammonia is the ammonium ion. The base dissociation constant Kb is 1.8 times 10 to the negative fifth. Look at a table on the right. It lists several weak bases with their structures, conjugate acids, equilibrium equations, and Kb values. As you see from the structures of the bases, some of them are neutral while others are ionic. The neutral bases must contain an atom with a non-bonding pair of electrons. The nitrogen atom of ammonia has one lone pair of electrons. Methylamine is formed by replacing one hydrogen atom with methyl group. Just like ammonia, methylamine receives a proton from a water molecule and forms a methyl ammonium ion, leaving a hydroxide ion behind. Ionic bases are the anions of weak acids or conjugate bases of weak acids. Hypochlorite ion or ClO- ion is the conjugate base of hypochlorous acid or HClO. The hypochlorite ion accepts a proton from a water molecule and forms hypochlorous acid, leaving a hydroxide ion behind. An ammonium ion NH4 plus is a weak acid and dissociates into ammonia and a proton. Take a note that ammonia is the conjugate base of ammonium ion. The Ka expression for this process is NH3 times H plus over NH4 plus. Since it is an equilibrium process or a reversible process, the reverse reaction is written like this. Ammonia accepts a proton from a water molecule and forms an ammonium ion and hydroxide ion. As you see, it is a base dissociation process. Then the Kb for this process is written as NH4 plus times OH minus over NH3. Let's combine these two chemical equations. Both NH3 and NH4 plus are cancelled, and surprisingly the overall equation is simply the autoionization of water molecule. Interestingly, if you multiply Ka by Kb, both NH3 and NH4 plus are cancelled, and you will get H plus times OH minus. This is the ion product constant for the autoionization of water, or Kw. In summary, multiplying Ka of a weak acid by Kb of its conjugate base makes Kw. This equation is another useful equation, since the Kw is the fixed value, which is 1.0 times 10 to the negative 14th. The Kb value of a weak acid can be easily determined if you know the Ka value of its conjugate acid. To maintain Kw value constant, and if the Ka value of a weak acid is high, then the Kb value of its conjugate base should be low. Or, as the Ka of a weak acid increases, the Kb of its conjugate base decreases. You may take negative log on both sides of the equation, then you will get pKa plus pKb equals pKw. which is also equal to 14. If you'd like to know the Kb value of a certain weak base, you may want to go to the library and find CLC Handbook of Chemistry and Physics. It is a very thick book with a hard cover. Unfortunately, you wouldn't be able to find the Kb value of weak bases directly from the book. Instead, you should look for the conjugate acid of that weak base on a very long list of weak acids, and you will be able to find a pKa value of the conjugate acid. Utilizing the equation above, you can convert pKa value to pKb. And since lowercase p represents negative log, you can easily convert pKb into Kb value. Acid and base react and produce salt and water in most cases. An example is that hydrochloric acid and sodium hydroxide react and produce sodium chloride and water. The salt NaCl ionizes into Na plus and Cl minus ions. Hydrolysis is a process of generating H plus or OH minus ions by the reaction of ions with water. An anion X minus is the conjugate base of an acid. If the anion is a conjugate base of a strong acid, then it has negligible basicity. In this equation, Cl minus is the conjugate base of HCl, and its basicity is very negligible and does not accept a proton to reproduce HCl. That is why we don't call it a base practically, even if it is apparently the conjugate base of HCl. Take a note that a single arrow is used for this process because the reverse reaction is not allowed. An ion that is a conjugate base of a weak acid retains non-negligible weak basicity. Here, acetate ion is the conjugate base of acetic acid. Acetate ion alone has some degree of basicity and accepts a proton from a water molecule and forms acetic acid, leaving a hydroxide ion behind. The production of hydroxide ion increases pH. That is why a weak acid like acetic acid is less acidic than the strong acid like hydrochloric acid. Polyatomic cations are conjugate acids of weak bases. Hydrolysis process of ammonia generates an ammonium ion and a hydroxide ion. Please be aware that the ammonium ion is the conjugate acid of weak base, ammonia. So the ammonium ion retains non-negligible acidity, and it donates a proton to water molecule and forms ammonia molecule and hydronium ion. The production of hydronium ion or proton decreases the solution pH. That is why a weak base like ammonia is less basic than a strong base like sodium hydroxide. Metal ions are mostly acidic, as you can see in this equation. Iron 3 plus ion receives hydroxide ion and forms iron hydroxide 2 plus ion, and leaving a proton behind. Exceptions are cations of alkali and alkaline earth metals, and they are not acidic nor basic. We will discuss more about it later. If both anion and cation are present, then the ion with larger Ka or Kb has a greater influence on the pH. Strength of acid depends on three factors: bond polarity, strength of bond, and stability of conjugate base. The first factor is the bond polarity that is caused by the electronegativity difference between a hydrogen atom and another atom that the hydrogen atom is bonded to. Let me take an example of hydrofluoric acid. The hydrogen and fluorine have very big difference of electronegativity, and this makes a very polar hydrogen-fluorine bond. The single electron of hydrogen that is shared with fluorine atom is lost to the fluorine atom due to the high electronegativity of the fluorine. This leads to the formation of proton and fluoride ion. That is how HF becomes an acid. The electronegativity difference between hydrogen and carbon in methane or CH4 is not significantly different. They share the bonding pair of electrons almost equally, making a nonpolar covalent bond. The hydrogen atom is not released from the molecule, and this is why the methane is not an acid nor a base. The electronegativity of hydrogen is 2.1, but the electronegativity of sodium is 0.9, meaning the hydrogen atom in sodium hydride is much more electronegative than sodium. Not like the hydrogen atom in HF, a single electron of sodium is completely lost to hydrogen and forms a sodium plus ion and H minus ion or hydride ion. This hydride ion is very basic. It further implies that bond polarity determines strength of acid of a substance. The second factor is the strength of bond. The point is that strong bonds are less easily dissociated. Let me take an example of hydrohalic acids. These are hydrofluoric acid HF, hydrochloric acid HCl, hydrobromic acid HBr, and hydroiodic acid HI. As you move down the table from fluorine to iodine, the size of halogen atoms increases due to the electron shell added one by one. Fluorine is the smallest halogen atom, and iodine is the biggest halogen atom out of the four halogens. The valence electrons of iodine is loosely bound to iodine nucleus due to the far distance. Hydrogen atom is also loosely bonded to the iodine. As a result, hydrogen ion in hydroiodic acid can be easily lost, making the hydroiodic acid the strongest acid out of the four hydrohalic acid. So HCl is stronger than HF, HBr is stronger than HCl, and HI is stronger than HBr. The third factor is the stability of conjugate base. HCl is a strong acid, and acetic acid is a weak acid. The conjugate base, Cl- is very stable, and its basicity is negligible, and it would not recombine with H plus ion to regenerate HCl, which is represented by a single arrow. However, acetate ion, which is the conjugate base of acetic acid, retains some basicity, and it is a stronger weak base than Cl- and does recombine with H plus ion and regenerate acetic acid, which is represented by a double arrow. In summary, the greater the stability of conjugate base, the stronger is the acid. Binary acids are the ones that are made of two types of atoms, one of which is hydrogen. Examples are HCl versus HF, H2S versus H2O. Which one would be the stronger acid in each pair? Obviously, HCl is stronger than HF because chlorine is bigger than fluorine. H2S is stronger than H2O because sulfur is bigger than oxygen. In summary, the greater the size of the element X, the stronger is the acid. In general, as you move from left to right in the periodic table, acid strength increases. As you move from right to left in the periodic table, the base strength increases. As you move from top to the bottom, acid strength increases. As you move from bottom to top, base strength increases. Certain acids have oxygen-hydrogen bonds, like sulfuric acid, which is visualized better in the Lewis structure. This is quite confusing because bases like sodium hydroxide also have one. How can you tell one from the other regarding acid or base nature of a substance that contains OH group? Here is a general structure. OH is bonded to an atom Y. If the atom Y is a metal, like sodium, then electrons are withdrawn to oxygen almost completely because metals are substantially less electronegative than nonmetals, like oxygen. This makes the compound basic because sodium and OH split, forming a Na plus ion and a hydroxide ion. If the atom Y is a nonmetal, then the bond between Y and oxygen would be likely a strong covalent bond because the electronegativity difference between the two wouldn't be high. Chances are it could be either acidic or neutral. It would be more acidic as the electronegativity of Y increases. Examples are methanol, which is neutral, and hypochlorous acid, which is acidic. Please be aware that chlorine is more electronegative than carbon, so it withdraws electrons along with the oxygen, and as a result, hydrogen is released as a proton. Let's take a look at these two acids of similar structure. The top one is hypochlorous acid, and the bottom one is hypoiodous acid. The OH is bonded to either chlorine or iodine. Which one is more acidic? Since the Ka value of hypochlorous acid is almost 1,000 times higher than that of hypoiodous acid, the hypochlorous acid is the stronger acid. How can we rationalize it? The chlorine is more electronegative and has more electron withdrawing power than iodine, and it explains why the hypochlorous acid is stronger than hypoiodous acid. In summary, as electronegativity of Y increases, OH bond becomes weaker and the conjugate base becomes more stable, which implies that ClO- is more stable than IO-. Acids like hypochlorous acid and hypoiodous acid are the ones in which OH groups and possibly additional oxygen atoms are bonded to a central atom. These acids are called oxyacids. As I mentioned earlier, acid strength increases with increasing electronegativity of the central atom Y. Please be aware that the hypochlorous acid has a hydrogen that is directly bonded to oxygen, not chlorine, but the formula is written as HClO. This is because of the convention that acidic hydrogen should be written first in the formula of an acid. Same principle is applied to HBrO and HIO. General trend is as electronegativity of Y increases, the Ka value increases, and acidic strength increases as a result. Another important trend is that acidic strength increases as the number of oxygen atoms attached to Y increases. It is like playing tug of war. If you bring more people and let them join your team will be reinforced and have better chance to win. Likewise, if an oxyacid has more oxygen in its structure, it would have more power to withdraw electrons, and it would become a stronger acid. As you can see the illustration, there are hypochlorous acid, chlorous acid, chloric acid, and perchloric acid. As more oxygens are attached to the central atom chlorine, it becomes stronger and stronger acid. Carboxylic acids are the acids that have COOH group or carboxyl group in their structures. The hydrogen atom in COOH is an acidic hydrogen. Acetic acid is a carboxylic acid that is made by joining a methyl group to the COOH. Similarly, benzoic acid and formic acid are made by joining benzyl group and hydrogen atom to COOH respectively. A carboxylic acid releases a proton and forms a carboxylate, which is the conjugate base of the carboxylic acid. The carboxylate forms resonance structures as you can see from the acetate ion. The resonance in the conjugate bases of carboxylic acids stabilizes the base and makes the conjugate acids more acidic. Please remember one of the three factors that determine the strength of acid is the stability of its conjugate base. The more stabilized the conjugate base, the stronger the acid. The acid strength of carboxylic acids increases as the number of electronegative atoms in the acid increases. This is because the presence of electronegative atoms in carboxylic acids help withdraw the electrons and distribute those electrons in the structure of the conjugate base. This would release proton more easily, making the acid stronger weak acid. Look at these two carboxylic acids. The first one is acetic acid and the second one is trifluoroacetic acid. Only difference between the two is that the second one has 3 fluorine atoms which are highly electronegative. Which acid would be stronger? Obviously, the second one is the stronger acid. The Ka values confirm it. The Ka of the second one is almost 10,000 times greater than the one of the first one. The third definition of acids and bases was suggested by Gilbert Lewis, and it is often called Lewis acids and bases. In his definition, a base is the one that donates its electron pair to something other than proton. The base is also called an electron pair donor. Lewis acid is the one that accepts an electron pair, and it is called an electron pair acceptor. In the reaction between ammonia and trifluoroborane, ammonia donates an electron pair to trifluoroborane. So the ammonia is a Lewis base because it donates an electron pair, and trifluoroborane is a Lewis acid because it accepts an electron pair. Let's take another example. In this reaction, a lone pair of electrons of water is donated to carbon dioxide that has 2 carbon-oxygen double bonds. Please be aware that a double bond is made of one strong sigma bond and one weak pi bond. The electron pair attacks the carbon, and that action breaks the pi bond in one of the 2 carbon-oxygen double bonds. This provides 3 lone pairs of electrons around an oxygen atom. That oxygen takes a proton from a water molecule and eventually forms this compound. This final product is carbonic acid. Carbonic acid is made by dissolving carbon dioxide in water. Most transition metal ions are acidic, and they hydrolyze water molecules. Here, zinc chloride dissociates into zinc 2 plus ion and 2 chloride ions. This zinc 2 plus ion receives a lone pair of electrons from a water molecule and leaving a proton behind. That is how the metallic cations are acidic, by producing protons. Hydrolysis reactions increase with increasing charge and decreasing the radius of the ion. It is due to the fact that The electrostatic interactions are proportional to the magnitude of the charges of the ions and inversely proportional to the ionic radius.